So we have already learned how to take derivatives. What we have learned is the meaning of derivative. It's basically the slope of a function at a given point, and the derivative function is the slope of a given function as a function of time, right? So there are two things: derivative at a point, the slope there, and derivative as a function, which gives you the value of the slope as a function of the points. Okay, and then we also learned derivative of a constant is 0, derivative of x to the n is nx to the n minus 1. We learned derivatives of trigonometric functions. We also learned that derivative is a linear operator, and we learned how to take derivative of a product, duv is udv plus vdu, of a quotient, d of u over v is vdu minus udv over v squared. And we learned derivative of a composite function. Basically, that was the chain rule. And then we also learned about derivatives of exponential and logarithmic functions. And now we will learn about applications. So the first one will be about related rates. So we're given a balloon whose volume is increasing at a rate of 2 centimeter cube per second. And we are asked to find at what rate the radius is increasing when the radius is 3 centimeter. Now we know that the volume is given by, or volume as a function of time. I mean, volume is a function of r, because it's 4 by 3 by r cubed, but r is a function of time. So if we take dv over dt, this will be the chain rule, so we'll get 4 over 3 pi, and derivative of r cubed with respect to t, so we get 3r squared, first with respect to r, and then with respect to t. Okay, so 3 and 3 cancels, and we are given dv over dt, which is 2, so this is equal to 2, and the radius is given as 3. This is also given. So dr over dt is simply dv over dt, 2, divided by 4 pi r squared, where r is 2, so 9. So 2 over 36 pi. Okay, so basically you have a relationship between two variables, v and r. Both are changing the function to of time. So we just took the derivative, applied the chain rule, and found the relationship. Next one, we have a plane that is flying horizontally at 600 feet per second. And at the moment, the position 3,000 feet. So x is given to be 3,000 feet. Okay, since it's flying horizontally, so we know that dx over dt is given by 600. 600 feet per second. X is 3,000. We have to find ds over dt. We know that s squared equals 4,000 squared plus x squared. Take the derivative of both sides with respect to time. So we get, using chain rule here, 2s, derivative of s squared with respect to s, times ds over dt equals, this is just a constant, derivative is 0, and we get 2x dx over dt. 2 and 2 cancels, and we have to find ds over dt. So ds over dt is x over s dx over dt. dx over dt is 600, x is 3,000, and s is easily found as s squared equals 4,000 squared plus 3,000 squared. So as a square root of this. Plug in and you find the solution ds over dt. Okay. Now a rocket launch. A rocket is launched, it rises vertically. Camera is positioned 5,000 feet from the launch pad. So this is 5,000 feet over here. Okay. Then the rocket is 1,000 feet above the launch pad. So the instant h is 1,000 feet. Its velocity, so dh over dt, is 600 feet per second. Okay. So we have to find this angle theta, d theta over dt. Okay, this 5,000 is fixed. So we know that tangent theta is given by h over 5,000. Theta is a function of time, h is a function of time. So let's take derivative with respect to t. So tan theta, we get secant square theta d theta over dt equals 1 over 5,000 times dh over dt. dh over dt is also given. This is 600. So the only thing we need to find is secant square theta, because d theta of dt will be this whole thing divided by secant square theta. And secant square theta is easy because we can find the hypotenuse here, which is square root of 1,000 square plus 5,000 square. And once we know s, we know secant theta is s divided by 5,000, right? And you plug in and you get the answer. Okay, so yeah, that's what's happening. Okay, now a water is draining from the bottom of a cone-shaped funnel at the rate of, so again, volume of a funnel, if you remember, is 1/3 of the volume of a cylinder with the same radius and height. Okay, so dV over dt is given. The height of the funnel is, total is 2 feet, and the radius is 1 feet over here. Okay, at what rate is the height of the water in the funnel changing when the height of the water is so many feet? Okay, so h is given. H is given as half, or 0.5. Now, when the height is half, the question is, what will be the radius? Okay, the height of the funnel is 2 feet. The top radius is 1 feet, so 2 and 1 is given. At what rate is the height changing? So dH over dt has to be found. But we also need to find, in this formula, what R is. So what we see is, if you look at these two triangles, right, this triangle and this triangle, they are similar, right? So H over R will be 2 over 1, 2. So H is 2R. That's the relationship between the two. Okay, so if we do that, we can replace R by H over 2 in the formula. So V becomes equal to, V is 1/3 pi. R squared is H squared over 4 times H, so this becomes H cubed. And now this is same problem as before. Take the derivative of V. V is a function of H, is a function of T. So if you take the derivative, we get dV over dt, whose value is given, equals 1/3 pi over 4, but this 3 and derivative of HQ will be 3h squared dH over dt. We know the value of H. Okay, we know the value of dV over dt, so we can easily find dH over dt is dV over dt divided by pi over 4h squared. So the trick in this problem compared to the other problem was that V was a function of two variables, but R and H were related to each other. So we could write R as a function of H, R H over 2. So then V became a function of only H, like the sphere problem where the volume was a function of only radius. So here we made the volume function only of height. Okay? And that will finish this section.